Thanks very much, David. And can you hear me okay?
Perfectly.
Brilliant. Yeah, it's an honor to be here. Thank you to the organizers, and it's been a really interesting and useful workshop. I'm gonna kick off with a very high level view of what I think a lot of us think really is like one of the most prescient thoughts in our whole field, which came from 1943, and I'm sure people at the time, at the verge of computing, were having really interesting thoughts, thinking what could happen. But at this point then, Kenneth Craik was pointing out that if an organism carries a small-scale model of external reality and of its own possible actions within its head, it is able to try out various alternatives, conclude which of them is best, react to future situations before they arise, utilize the knowledge of past events in dealing with the present and future in every way to react in a much fuller, safer, and more competent manner to the emergencies that face it. And to me, just coming out right now of Raquel's talk and Wolfram's before that, and even all the way back to Luca's, I think everyone can see the hints that on top of effectively a predictive model of our external reality, then great things like model predictive control can happen. And then it gets interesting because the divergence as per Wolfram, or difference between HD maps and versus no maps, starts to emerge. How much of that model can be carried in our robots or AI heads versus actually can be a shared and, if you like, the next generation of HD models. And that's a lot of what I want to talk about today. So we have this thought, and I think it's shared, which is that actually a worldwide shared, dynamically updating, physically predictive model of reality that is built and kept up to date with reality by all mobile observing devices would be a key enabling factor for superhuman, ultra low power, robotic and AI AR perception in our world. Now that's a mouthful, but all I'm saying is sort of like some 70 years later from Craik, 70 plus years later from Craik, that actually seems like the right idea. And the question is, if one robot, can have a predictive model of its reality and find that useful, at some point, then robot sharing those models become really obvious again, except at the moment that we have this complex problem of how to share like a sufficient model for various tasks, etc. However, let's think of this as a holy grail, much in the same way that artificial general intelligence is for AI. This can be a sub-goal of AGI on the planet Earth. And why? Why a shared model? Why physically predictive? Well, ultimately, as Craik says, because we can then predict what-if scenarios. But also, there's a point in there where I talk about ultra-low power, and it gets past this point. Once you've got a system that is so low power, and I'm going to introduce today ARIA, where we have to work in the milliwatts regime for our systems, then actually the only way of having this kind of perception capabilities that are necessary for an always-on, for example, contextualized AI assistant, is to start to use essentially the sensor data and the compute that's there, not to directly infer things about reality, but simply to keep a shared model up to date, or alternatively do away with the features that we care about. So it's actually a fundamental point that at some point of low power, and low power being form factor constraints, compute constraints, power dissipation constraints, actually you need a shared predictive model, because you need other devices compute and other devices sensing capabilities and your own to effectively build and keep up to date a consistent model, which then we will claim you can query effectively. Now, the next question is, could it be semantic free? Why? Well, semantic free, we mean in the same way that in Luca's talk, he showed great semantics laid on top of what was a physically predictive surface model. The thing is that kind of introduction of semantics also limits the potential for what is represented. And actually that was pointed out by others as to why we might want to move away from shared maps and HD maps as an example. But what about this holy grail? What if there was a physically predictive representation that could be kept up to date that didn't need to introduce the notion of, for example, a code can? And in some sense, that might be possible. And then we could layer on top of that semantics. But it's certainly a chicken and egg right now. And there's a whole ton of other things, completeness of the model. What does that mean? What do you represent and not? Can it be really consistent so that you can trust it across devices? And what about privacy? What's the granularity of representation? So many big questions. So I want to start with, first of all, just thinking through a space of predictive models of reality. And actually it starts with just thinking about the space of all possible raw data that a device or multiple devices, think about, let's say, the millions of future self-driving cars and AI devices that we're wearing our wearables on our heads, you could just think about that space and somehow capture it and then somehow query it at runtime, and you'd have all sorts of problems with like how on earth you did that because of problems of communication bandwidth constraints and other problems associated with how you'd even store that kind of data manifold. So we think about, well, a sensory compressive predictive model would certainly take all that data, which is the only data there is to build any other type of model, by the way, that's why it's there, and compress it. And that compression must have learned something about what was common in the structures. We can go one step further and we'll call that sensorially predictive, which is where you can think about a model that we've built where you can ask for a space-time query of that model for a given sensor modality, and it will predict back what the thing would look like or sound like in that time and space for that particular modality. That's certainly getting really valuable, and it would be an awesome ultimate compressive mechanism. And if we could just push observations into a sensorily predictive model, that would already be super useful because it would drastically reduce the need for all the problems associated with using the raw data and enable mobile limited devices to actually have access to a sensorily predictive model when they do not have that capability on board because, for example, limits on their lens size or compute capacity. As we go one step further, I talked about physically predictive to begin with, and that's different from sensorially predictive in that it introduces the notion of actions on the model, such that if an action in the simulator or predictive model was to be performed, then actually the sensory prediction would predict what would happen if you had performed that action in the real world. And so just a point here, every model we're talking about here is not just any model of reality, it's the one that maps to our model of reality. So a physically predictive model of reality, you could add a force and apply it, and the sensor prediction you get back from a space-time point for a given sensor modality would look like what you would actually see in reality. That would be incredibly useful. In fact, we claim this is the key thing to really be solving. On top of that, though, is where it actually starts to get useful for most given tasks. Given a task, you can start to introduce a taxonomy and a semantics and an ontological ladder about what those things are and why they're important, and also like perhaps highlight things in a more computer memory efficient way. And that's probably what we see happening actually in the loops of people optimizing for self-driving cars and other tasks, is that you introduce the semantics as soon as possible, i.e. I don't need to represent everything in self-driving cars, but I do really need to get the pedestrians and the road's really important and so on. And so, on the other hand, like, a grain of sand and a particular ice cube in a jar for a sunny day's drink is not important for a self-driving car. Semantically predictive isn't the same as pragmatically predictive. And actually, Luca, at the beginning of this workshop, introduced something which would require pragmatically predictive models of reality. When asking your robot to get you a coffee, it would also need to know when it was relevant to not get you a coffee and get you just a cup of tea instead, because either the coffee was not the type that you like and or there was no coffee, but there was tea, and it knew that what you wanted was the drink because you're thirsty. All of that is really not about semantics. It's actually about pragmatics. And that's an area which I think like very few teams are really doing, especially when you see the span from effectively working with just raw data and doing inference there through to building physically predictive models. There's a giant span that we need to go through. So we're interested right now in physically predictive models. We've been building one for quite a while, or at least the technologies underlying it. It's called Live Maps. It introduces the ability to take data from various different devices, including pro capture rigs, seed maps, and build different layers. Those layers begin with localization. Solve localization, you have a space-time frame of reference, wherein you can start to cache physical structure about things that are there without knowing what they are, and you can certainly start to track them without knowing what they are. You can layer on semantics if you know what they are, and you can have the difference between instance level and class level semantics, very important for given tasks. All of that stuff intermediately we'll call the real world index. We think that's super valuable. Certainly, the potential for being able to index reality and search real world reality with a semantic sense. Real world physical search seems super valuable as an underpinning of the future of AI and robotics applications. And all of this is useful for us doing AR, well, fundamentally because you can anchor virtual content and query and merge, build a bridge between physical and virtual realities. What we claim is that if you build a model like this, then, given a location of a device, you could literally just query the current state of reality. And that state doesn't need to just be, say, a rendering of the thing photorealistically. It could be literally render other underlying physical properties that are directly being modeled. that your live device has no chance to infer in real time. And so that chasm that currently exists between how do you bootstrap such a model, such that when there are millions of devices, then actually the problem is updating, not building the model from scratch. You've already been in your home 1,000 times. It's updating the model and keeping it up to date. When someone visits your home or when you buy a new robot, why wouldn't it want access to that model, given all of the other things that you can do with such a model, such as put privacy constraints on certain regions of it, share parts but not others, etc. So we claim this actually is the paradigm, the framework within which we really should be working towards. And we realistically, over the past 6 years, have been working our way from location through physical modeling all the way up through dynamics. And today I'm going to introduce a new type of work that we've been doing in physical modeling and dynamics modeling and location that is strictly at this problem space of dynamic real world environments. So the key areas, and I'll cover each of these topics with one subject in the talk, are, well, we have to work on devices because there are physical limits on mobile sensing, compute and communication, as we've talked about. Location, because we fundamentally believe that the notion of a space-time reference frame in reality is true, independent of the content. And then index, which is what we've just talked about in terms of the physically predictive, semantically predictive, and other predictive components of reality. In the talk today, I'm going to basically introduce Project ARIA to talk about a certain class of devices that we've introduced. These are devices that are now available for partners in academia and industry labs, where we're simulating with this device what the future of an augmented reality class is, always on devices like. So it's a lightweight wearable. It helps us get a new view of ego-centric data. I'll then talk about a new type of tracking that we introduced called TLIO, which solves some of the problems with getting a frame of reference with very high quality without using cameras at all. And that's important for solving problems when you're in highly dynamic visual environments. And then finally, I'll introduce this work that we've been doing on predictive modeling using passive camera data. And hopefully it all makes sense in this scheme of effectively we're trying to build a model and keep it up to date. These are just parts of the technology stacks that are needed. Okay, so first of all, Project ARIA. So we were motivated by understanding the fact that there's been this revolution of building maps, and HD maps is another example of that that's used for driverless cars. They themselves sat on top of actually the ability for low-flying aircraft and satellites to go and map top-down Earth, and then for people to annotate road networks, etc., building polygons and so on. For a given city, you can have, say, a satellite covering pretty much all of it, at a resolution where if you work out for a diffraction limit for a particular size of lenses that can sit up there, is pretty good, on the order of like, tens of centimeters. It's certainly not going to look indoor though, so it's outdoors only. And because of the kind of like flight paths that these devices take, typically you're not going to be capturing lots of dynamics unless you really start to plaster the sky. Although some companies are doing that for logistics, and so you can start to get dynamics of outside vehicles using satellite driven data. After that, then basically car-based rigs started to build maps and backpack systems. And we built, this is an example of one of our own backpack systems that we've been using for prototyping live maps infrastructure. And those together start to get at, more scale in inner cities at higher resolution because you're closer to the action. You're still not indoors with cars. With backpacks, suddenly you are indoors. And so you can go into all sorts of malls and airports and so on and start to build useful navigation maps. And of course, like our colleagues in Google pioneered a lot of this, and it's really very valuable if you're doing things like navigation. Backpacks cannot get you to the action and at the level of quality of humans interacting with the world. For that, you need a wearable device, and we claim that effectively the future of building a physically predictive map or model of reality and keeping up to date is going to come from these type of wearables. Okay, when you've got a device like that, you can really start to capture everywhere. And the thing here is to think about not when there's only one device, but when there are tens of millions of devices. And then we're back into this regime where you really want that device to be able to give you, for example, the best assistance possible, the best navigation possible. But as Wolfram pointed out, that device is compute limited, as cars are. This is even more so by a couple of orders of magnitude, let's say. And it's also sensor limited. So the only option you have is to think in this regime of if you have hundreds, thousands, millions of devices and you have bootstrapped a model of reality, then the data from this device can keep that model up to date, and then you can use that model to basically sense reality. ARIA, and we've got a web page you can go to for some more details on this, is basically an all-day wearable computer, less than 70 grams needed, so you can wear it all day. It's got a 1.5 hour continuous recording time without needing to be plugged in. Super valuable because the form factors have been designed so that effectively you can pretty much walk anywhere. We haven't tried to obfuscate the lenses or anything like that, and we'll talk about some of the features for making sure people know that when we're recording, but it's a pretty hefty beast. It basically has a lot of the same things in that our headsets do for VR, but shrunk into a glasses form factor. And so this includes 2 SLAM cameras, a very high resolution RGB camera, effectively similar to a GoPro, 2 IMU systems, GPS technologies, and a ton of other things that we'll talk about here in a second. What I want to tell you about is it comes with a companion app. We've done that so that users can control when recording with such a device is happening and be able to control uploads to servers where we then automatically obfuscate any PII, privacy, potentially violating information, faces, number plates, etc. And you can also start to say which recordings you want to be shared to your research community. So this is something that we've done for Facebook research at scale, so that we can start to get really the kind of data that's at the point of view of humans and start to do so within a way that's controllable for those people that are sharing that data. We have a recording LED and also a switch that allows you to turn on and off the recording at will. There's also eye tracking on the device and a spatial microphone array. And this is very exciting because with eye tracking, I should say exciting and also certainly disturbing if we don't get the privacy side right, which is why we're doing this early before products are in the market. Effectively, with eye tracking in SLAM, you can start to get world-locked eyes, and that's very important for intent. The device is quite complicated, but ultimately it's in the realm of achievable for our organization. Really excited to see partnerships emerging with folks who want to use this for data for good. We also, like the t-shirt I'm wearing, make sure that we're telling people that we are recording when we're recording, although I'm not wearing the device right now. And that makes sure that there's a consent capability for bystanders when we are doing that recording. And there's also policies in place so that they can effectively have any recordings deleted when we're in public. So this device simulates the data streams that will allow us to research areas of machine perception before the products are in the space and allow us to work with different partners in different focus groups in public and in academia and industry to really find out where the pain points are, not just in technology, but in privacy and trust as well. Now, back to the technology point, when you've got such an ego-centric device, take SLAM cameras, data rates start to become very interesting to think about. This is a recording device, and we do research with it. But think about this. If you've got SLAM cameras at around 640 by 480, 20 frames per second, and 10x compression, and a ton of other sensors with relatively reasonable compression, these are relative compression standards that are achievable today. And for a SLAM system, compressing at 10x with JPEG, your SLAM system will still work pretty much fine. That's on the order of 0.9 terabytes of data per day, an 8-hour day. Multiply that through by, let's say, 100 interaction people over a year, and you've got 30 petabytes of data from this type of device. It starts to become really challenging to think about how you deal with that data in terms of data sets that you were really proving were like doing what you wanted them to do. And reasonably, when we look back at like, well, what about compressing them better and so on, getting to a sensorially predictive model seems very valuable for this reason. And of course, in some sense, what we're claiming is that if you were to be able to have a simulator, and of course, lots of teams now use simulators, as Raquel was showing, if that simulator was to overlay reality, and if it was being essentially sensorially predictive of reality, it would be massively compressive and also very useful as a prediction mechanism for running algorithms within. How else could you do it is really the other question. Okay, onto visionless tracking. Now, if we're going to be able to take mobile devices and build a model of reality and keep it up to date, we claim that one of the key technologies you need is location everywhere. Location everywhere does not mean violating privacy, though. It means we have to solve for technologies where tracking is everywhere without violating privacy. And so one of the exciting areas that we've started to look at is IMU-only navigation, so that there is no risk of any of the data streams actually having access to potentially PII violating observations. This work was actually taken by looking at where we'd already got to, and by we, I mean the industry and academia, in solving the device localization problem, which starts with GPS and goes through Wi-Fi positioning systems, visual positioning systems where you've built pre-maps, SLAM systems, and VIO, visual inertial odometry, basically have to be the always-on component, so you can get super high accuracy on the order of millimeter precision. For the applications that we care about in AR, we need millimeter precision and better, because we need to be able to world lock virtual objects as if they are really there. But also, if you have such a mechanism, then it becomes an incredible indexing mechanism for reality that allows you then to cache things like physical structure with very high precision and read it back again. So when you've got a VIO and a SLAM system that's as accurate as that, it becomes sort of the underpinning for how to think about the frame of reference, the space-time frame of reference, on top of which everything else is cached. However, it uses visual sensor data. Here we see an example of ARIA and the data being used through our VIO pipelines, which is effectively a version of an MSCKF system. And it's very, very robust. It does the job. And we're really interested in, can we get the same performance, but without needing the cameras? Why? Well, partly privacy, partly because of lowering the power as well. Using 20 frames per second or even 10 frames per second data is very prohibitive on an always-on device. Well, where does it need to work as well? Because visual data is going to be limited in certainly super high dynamic range environments, day-night conditions, indoor-outdoor environments. If you're relying on features and maps that are pre-trained or only basically stable in certain environments like indoors, then you're going to have problems with systems that are built based on visual systems. And there's also the visual not equal to inertial gap, i.e. when I'm in a car and driving around, then I've got this frame of reference difference between my dashboard and what my glasses might be seeing and what they're seeing outside. And we at least need to know what the real inertial frame of reference is versus, let's say, what the visual frame of reference is. For example, the relatively static dashboard or table in a train relative to your true real world movement. And so that's what we're really interested in solving for. So IMUs, of course, have been around for a long time. They're in all your phones. And effectively, this area called Strapdown Navigation says, look, why don't you just double integrate the accelerometers and integrate the angular velocity? So accelerometers into velocity, into pose via continuous rotations under gravity alignment, then you can get position, right? Well, because of the different types of noise, then even over a relatively short term, what we call long term error here of 30 seconds, you're looking at on the order of integrating to 3.5 meters worth of drift with such a system. Hence why visual updates in visual inertial odometry are typically critical. Well, that was until folks effectively demonstrated that you could start to use machine learning to replace what historically had been the priors on pedestrian dead reckoning techniques for IMU only measurements. The idea here is that if you can build a prior model as to what type of motion is going on, then you can constrain that drift. And so what our team has done is use the type of data that we've got from our VIO systems. These are thousands of hours worth of VIO and SLAM data from Ego-centric headsets, and be able to train a new model built from the basis of the Ronin system that was introduced in the previous slide. The way that works is effectively to build a neural network, which is a version of a ResNet, and literally have it input the gyroscope and the acceleration data in a gravity-aligned frame of reference, and then predicts outward just the translational displacement with an uncertainty, and put that into a standard EKF, as a standard, into a version of a multi-state camera filter, and fuse that. And it turns out to work extremely well. And this, for anybody who's tried to doubly integrate or do effectively the type of integration-based navigation odometry introduced previously, is an insane thing to see. But it turns out it works quite well. So what you'll see here is a version of VIO in green, a version of our 3D upgraded Ronin. The original works from Phil Cower's lab was in 2D. And then TLIO, which is the tight-learned inertial odometry, which is this neural network feeding essentially the EKF with displacement estimates. And you'll see this over hundreds of meters of trajectory. Both the 3D Ronin and the TLIO don't really drift, and yet it has no access to the image that we're showing here. It only has access to the IMU. The difference really between 3D Ronin and TLIO is you'll see that TLIO includes all of the high frequency motion that the full VIO system does, because it's using a proper statistically correct EKF to estimate the motion. You'll see that even here, as we stand at the wall and effectively write, that these systems that are relying only on IMUs are not drifting. So this is an incredibly surprising result, because the power consumption on such devices is, well, whatever your VIO system was, minus all of that sensor data, the bandwidth to it, the computing of features, feature pyramids, etc., detection and matching, etc. So this is revolutionizing where we're looking for actually the next solutions for always on tracking. Just a quick example here of walking up and down some stairs in 3D. Pretty inspiring to see it happening. Again, VIO with access to the camera data in green, and in blue, the TLIO. Over 10 minutes, the drift doesn't seem to explode. As you can see here, we're looking at on the order of, at worst, a meter worth of error over a 10-minute trajectory. And in a couple of dimensions, it's actually really surprising how constrained it can be. Do visit the webpage for more information there. So on to the final section, which is towards predictive models. Here I'm going to introduce effectively what is a solution in the making to the point that was noted in the workshop introduction, which is that artificial agents struggle to interact with complex and dynamic environments. From the perception side, we know that too well. And in fact, we worked for so long on building, as what we were thinking, visually predictive models as possible. But realistically, these models, Replica is the example I'm showing here from our work in 2019, they're static. And although they are very beautiful and they have lots of visual predictivity, and if you want to, you can train your robots in there. And we did that in collaboration with the Habitat team in our FAIR sister group at Facebook. And they're certainly good for that. If you can build a model like this, then you can use it for training an agent. Realistically, this model is not being kept up to date. It's not dynamic. Certainly, we push the state of the art with static reconstruction, but as this workshop suggests, that is not sufficient. And as semantically predictive as the thing is, realistically, the real problems to solve for now are dynamics. Now, all of that was using this type of camera, which is a structured light system with sort of a very special reflector detector so that we could get where the reflective surfaces were and so on. And then 1 year later, the NERF revolution happened. And so I'm not sure how many people on the call are really familiar with NERF, but I definitely want to give a very flash overview before getting into our work, which is built on top of this, to take what is NERF, a static reconstruction for a view synthesis, through to the dynamic realm. NERF was a revolution because using purely passive data, it can get this level of reconstruction accuracy. What you're seeing on the left is a predicted rendering given a query pose, and a predicted depth map given a query pose from the underlying model, which is actually captured entirely within a multi-layer perceptron. The system is effectively a multi-layer perceptron based around things like DPSDF, but crucially introduces this notion of position encoding. So the network inputs basically a position of a sample ray that you're interested in querying what the value of a position in a volume should look like. There's no actual volume explicit here, it's in a multi-layer perceptron. And then you train that multi-layer perceptron weights to effectively predict under integration of that ray, what effectively a training image sees. So given training images that are sparsely sampling the scene, then with some holdout test images, then you can essentially build this MLP to predict what the underlying mapping, the 5D planoptic function should be, which goes from spatial location and viewing angle directly to a volume density and view-dependent irradiance value. Now, here's an example of us using that technology from 2020 on NERF data, low resolution. And this is a model of a very big apartment that we've done using the technology. It's obviously not as good as the sort of underlying high-res bespoke capture that we demonstrated before. But actually, all that was done here is that we ran the SLAM system on ARIA data, and then with a very low resolution version of the RGB camera data, just train that model, and that was it. Whereas if we were to, well, actually you can see the paper for the replica dataset system, there's such a number of stages to be able to capture different effects that are going on. Okay, that's again just static though, right? What about dynamic scenes? Okay, well, I'm going to shift a little bit from the kind of ego-centric headsets back to rigs that look more like the sort of thing you might put on a car. We need to be here because we're at this beginning of a new revolution in NERF-like representations to represent fully dynamic scenes. So we've been able to show, and this is a submission that's gone in recently, called neural 3D video synthesis. The model we call DimeNerf basically extends the NERF model introduced previously into full video systems. It's capable of capturing the various different transparency, volumetric, steam and flame effects, shadows, and of course, dynamics in the scene. What's fascinating is that, again, the underlying model here is completely implicit. So we just train a basic multi-layer perceptron to basically say, give an array, and in this case, we're going to also condition it on a time latent space code that we'll talk about in a second. Just give us back, the value for this planoptic function query. What we're seeing here is the underlying prediction of depth or density at the point at which the implicit surface says this is probably where a surface is, although there's no actual explicit representation of the geometry in this setting. We've trained it and tested it indoors and outdoors, and it's really fascinating to sort of see the quality of reconstruction. So here you're seeing a virtual camera querying the predictive visual model and getting back a smooth trajectory, even though there's only 17 active cameras in that rig, and also getting depth maps like this are purely passive data capture that extend from the near field to the far field, which is challenging for any other type of sensor modality. So it's really revolutionizing, these NERF type models are really revolutionizing the ability to build geometric and photometrically predictive models of reality, even though there's nothing explicit about the underlying representation. So what we've done is extend NERF light fields to include these latent space time codes. And so we now map from a positional code and direction and this latent code to the color and density value. The difference, you might say, well, what about just training conditioning just on time versus a latent code? Well, this is the difference in that case. So we use hundreds of variables for our latent Z codes for each frame in the style of deep SDF and its latent code embeddings. And you can see here the difference with just basically adding a T time variable for querying and training with time for each frame in a standard static NERF system. A couple of things you need to do if you're going to train models that are this big, because otherwise there are billions of rays. So you can do effectively keyframe training first, sample keyframes, train it on keyframes, and then extend to the full sequences after you've converged on keyframes. And also, very important was ray sampling strategies. So looking at the fact that you can tell whether or not a pixel is changing over time in its view value allows us to say, hey, put more samples in the batch for the neural network training there versus there. And so we can go from on the order of billions of rays that are needed to sample just a 30-second volume of this type of data through to just thousands of rays. And that still means week worth of training, but versus a lot longer than a week. This is just a quick example of that.
Richard, we should wrap up because we are running out of time.
Thanks, David. So I shall wrap up. We've got some examples. Please see the papers there. So that's an example of effectively sensory predictive, but physically predictive. I'll leave you with the fact that really a NERF scene can be decomposed into a background and foreground objects. And we've got a paper that's in CVPR that tries to do that, factorize essentially NERF fields, dynamic NERF fields into these rigid objects plus background. Really, this is the beginning of getting at physically predictive, because once you've got that, you can start to recompose scenes back together and predict what if this actual degree of freedom of that thing, which has emerged, actually was over there, for example, much like a scene graph composition. Okay, skipping that and in review, it seems like tracking is starting to work pretty much anywhere we want to, and that is a foundation of space-time frames of reference, on top of which we can start to look at new representations for physically predictive models of reality. I'd like to leave us just with a point that really looking at distributed sensing, compute and memory access across devices and infrastructure, thinking about algorithms that can exist across this entire space is very exciting. And certainly Davida has been working at the sensor end through to the edge-based clients, and other people on the call have worked through cloud and other sorts of infrastructure scale mapping systems. It's exciting to think about that full stack and how it's needed to build a predictive model of reality. Thanks, Davida. Back to you.
Thanks a lot, Richard.